no. Anyway, I do have a problem with Polish names. They're so hard to pronounce. Yeah, she actually did her undergrad at McGill, so she's like coming back home. And yeah, with that, like I'll let Marta talk about plasticity and continual learning. Thank you. If yeah, I think it'll make it easier if you.
All right, hopefully the people on Zoom can hear me. Yeah, that's better. So hi, everyone. Thanks for the intro, Razvan, and for making a very good attempt at pronouncing my supervisor's last name, which I still often mess up, despite having been her student for like 4 years. But yeah, today I'm going to be talking about why neural networks lose plasticity. So this is a conference on lifelong learning, so hopefully a lot of the motivation for that is already like pretty obvious. But I'm going to start off this talk with a few definitions, and I'll get to the motivation immediately after, but if you just bear with me through this. So because plasticity is a pretty overloaded term, it's used in neuroscience. We have started to use it in machine learning. I thought it would be good to just quickly look up what is the definition. So I pulled up Merriam-Webster and got this very useful definition 1, which is that it is the state of being plastic, which was not helpful at all. I went to the second definition on Merriam-Webster, which is the capacity for continuous alteration of the neural pathways and synapses of the living brain and nervous system in response to experience or injury. That also is not useful for us because it's explicitly about living systems. So for the purposes of this talk, I just made up a definition, which is the ability of a learning system to adapt to changes in its environment or objective function. So this is the rough definition I'm going to be using throughout this talk. So when I say plasticity, I am not referring to real brains. I am referring to a more abstract general learning systems. So now we can get a little bit into the motivation. So, I mean, I'm at a conference on lifelong learning agents, so hopefully people are already somewhat motivated to study systems that can continue to learn throughout their lifetime. But to give a few examples of how this might turn up, one very simple example is sort of curriculum learning style approaches that we often use in humans. So if you've ever learned how to drive, you probably did not start off learning how to drive in a snowstorm. You probably started off learning to drive on good weather. Maybe once your parents were convinced that you knew which pedal was the gas and which pedal was the brake, they let you try driving in the rain. And then after you could confirm that you didn't totally slide off the road, they'd let you drive in snow. Now, when you learned how to drive in good weather, that didn't stop you from being able to learn how to drive in snow. But as I'm going to get to in this talk, a lot of the issues that come up in sort of machine learning and plasticity happen because training a neural network to drive in good weather can bake in sort of spurious correlations or bad inductive biases that can, in some cases, stop it from learning how to drive in snow. So that was a very abstract example. No one is actually, I think, currently trying to test the ability of neural networks to sort of transfer from good weather to terrible weather all in one shot. But we actually sort of, even in our current benchmarks, often see forms of quite drastic non-stationarities. So a really simple example of this is found in the Atari benchmark, which I'm sure a lot of you have run experiments on. So if you go to the game called Enduro, there's this really weird thing that happens, which I only noticed when I was watching a YouTube video of it, which is that as you're driving along initially, you sort of have this green road that you're trying to follow. Then randomly at some point in like the middle of the game, all the colors switch and suddenly you're driving on a white road. So ideally, you would be able to pretty easily generalize from whatever you learned on the green road to whatever you learned to being able to drive on the white road. And you would hope that learning to drive on the green road in particular wouldn't stop you from being able to learn how to drive on a white road. And then finally, one sort of more compelling example that I think is going to become more prevalent as time goes on is sort of the use of like very expensive to train systems on data that changes over time. So if you are training a model from scratch, say to do some sort of fashion recommendation, I mean, fashion changes very quickly. If you took a model that was trained in the 1960s and tried it to recommend clothes for teen kids in 2008, that would not be a very successful model. But it might have been very expensive to train, and you might not want to have to train it from scratch again when you go from the 1960s to 2008. So one challenge that I think is going to become a lot more pressing in the near future is sort of how do we enable learning systems to adapt to sort of distribution shifts without needing to train them over from scratch, as training them over from scratch becomes more and more expensive. So that's a bunch of examples of why we might care about maintaining plasticity. It's also worth noting that this is basically like maintaining plasticity of neural networks is like super fundamental for making sure that they can deal with non-stationary and changing distributions. So the way that I first sort of came into this field was when I was training agents on Montezuma's Revenge. For those of you who aren't super familiar with it, Montezuma's Revenge is this super sparse reward Atari game where you basically have this character who is navigating the world, and there's like a million ways it can die. And in order for it to even get its first reward, it has to go pick up a key, move that key to the other side of the room, use it to open a door, and then go through that level. This takes quite a lot of random exploration to get your agent to do. And what will often happen is that basically agents pretty much never take off. And initially, most people sort of think of this as a hard exploration problem, and a lot of approaches that are evaluated on this method tend to just look at how do we improve exploration. However, part of the problem as well is just that oftentimes if you train a neural network to predict 0 and it gets really, really good at predicting 0, actually the best way to do that is to saturate all of your ReLU nonlinearities in some layer of your network, because a saturated ReLU outputs exactly 0. And then it doesn't matter what your final layer weights are, you're going to get 0 training loss if you're not getting any reward. So that's great for the purposes of minimizing your TD learning objective on your current task. But it means your network can't propagate gradients anymore. And even if you do see a reward, you're not going to be able to use it. So this was sort of the first really compelling example I saw where there was something happening in a neural network that was stopping it from learning. And because it wasn't able to learn, it actually turned out that in some cases, it was seeing enough reward that if it hadn't lost plasticity, it could have picked up on that reward to improve its policy and actually score some points in Montezuma's Revenge, even without any fancy exploration. But because it basically wasn't able to change its predictions anymore, it was just stuck in this regime of not getting any reward forever. So it's worth noting that like it's not as though loss of plasticity is this particular pathology of neural networks. I mean, it's very widely known in dog training that it's usually easier to train a younger dog than it is to train an older dog. I will not use the cliched expression in this talk, but you all know what I'm thinking about. So this is sort of a phenomenon that seems to be pretty universal across all of the systems we know, biological and artificial. There's maybe an exception in the form of a particular species of jellyfish, which doesn't really have a brain, but it does have a neural network. It can like totally like revert to a baby and then grow again in times of environmental stress. That jellyfish probably doesn't exhibit plasticity loss after it recycles itself, but that's a very rare exception. So the rough outline of what I'm going to be talking about today, I'm going to start off with defining and characterizing plasticity in neural networks, just to make sure we're all on the same page when I say this network lost plasticity. What do I mean by that? I'm going to dig into some of the mechanisms by which neural networks can lose plasticity. I'm going to discuss a lot of works which many people in this room have written that propose some partial solutions. And then I'm going to discuss sort of what are some exciting open questions that people who are interested in this area might want to work on. So yeah, we're going to start off with sort of defining and characterizing plasticity in neural networks. So this is a quote from Quine that I really like. I've stolen it from my colleague, David Abel, who likes to put this at the start of all of his talks, which is that the less a science is advanced, the more its terminology tends to rest on an uncritical assumption of mutual understanding. So to make sure I'm not resting on an uncritical assumption of mutual understanding when I talk about plasticity, I'm going to get into some hopefully not too boring technical details on how I'm defining and measuring this quantity. So typically when we think about plasticity in neural networks, a neuroscientist would think about the ability of the brain to form new connections. This is a kind of useless definition for the purpose of neural networks, because we usually train with a fixed network architecture and just vary the strengths of the weights. So we're not actually adding new connections into the network. So by the definitions that most people would use in neuroscience, no deep neural network really has any plasticity because it can never make or change its connection structure. So ideally, for our purposes in machine learning, we want some quantity which sort of depends on the learning algorithm we're using. So the plasticity of a neural network might sort of change depending on whether we're optimizing it with SGD with step size 1,000,000, which it's probably never going to learn anything, or versus Atom with step size 0.001. It should depend on the neural network architecture and the parameters that we're starting the learning algorithm from. Ideally, we want a quantity that's sort of higher when the network can quickly learn new things and lower when it cannot. We would ideally like it to sort of depend on changes in what the network can output. So we don't want to necessarily just restrict ourselves to looking at some quantity that's happening inside the network. We care ultimately about the network's ability to learn new things, which is a property of its outputs. And we ideally sort of want this to depend on what class of new tasks we actually care about the network being able to learn. So for example, we often say like human babies are very plastic, but even a human baby would never be able to do something like, you could never train it to sniff out bombs. That's just like not something that it's really capable of. So when we evaluate human babies on the basis of their plasticity, we're kind of talking more about there's some set of tasks that we actually care about and that we think is relevant for a baby to be able to do. And if we say its brain is very plastic, we're implicitly restricting ourselves to plasticity with respect to this set of tasks. So because I'm going to talk a lot about how neural networks lose plasticity, that sort of implies that I'm measuring some quantity that's going down over time. So I'm going to give a quick overview of how I'm measuring this quantity and what the y-axis is going to mean on a lot of the slides that I'm going to be showing later. So the overall idea is that we're going to measure plasticity by checking how quickly the network can solve some set of new tasks. So for example, we might have some set of regression data sets, and we're going to sort of test the network on all of these regression data sets and say, if I run SGD for 500 steps, how low do you get your loss on this particular regression data set? So the idea is we're going to fix some optimization protocol O that's going to go from given some data set and loss function and some initial set of parameters. It'll give us some final set of parameters. We're going to pick some starting set of parameters. So we might take a network's random initialization to start off, and then compare later some checkpoint from its optimization trajectory. We're going to randomly sample some sort of probe learning task from some distribution we care about. And then we're going to run the optimization protocol from the starting parameters on this data set and evaluate the loss at the end of training. So if a neural network is sort of not losing plasticity, we'd expect that if it can perfectly interpolate some set of training tasks when it's randomly initialized, it should still be able to perfectly interpolate them after you've trained it for a while. If you run the same optimization procedure from this later parameter checkpoint. I'm just going to pause here to make sure this sort of protocol is pretty clear. If anyone has any questions, you can either go up to that mic or raise your hand and ask, and then I'll just repeat it into the mic. Otherwise, I can move on. OK, cool. So this procedure basically gives us a nice sort of formula that we can use for measuring plasticity. So we're basically going to say the plasticity of some parameter checkpoint theta t is given by some sort of baseline, like equivalent to sort of say, if we predicted the mean of all the probe tasks, what loss would we get, minus the loss we actually get on the probe tasks after we've run our optimization procedure from that set of parameters. So the idea here is that we sort of have a few desiderata that we listed out before, and this procedure kind of meets all of them. So it's going to depend on the optimization algorithm, the parameters, and the network architecture. It's higher when the network can quickly learn new things and lower when it cannot because we're subtracting the loss. So if we'd lost so much plasticity that all we could do is like change the bias in the final layer, then it would basically get loss equal to whatever our baseline was from, for example, predicting the mean. So its plasticity as we're measuring it would be 0. If it was able to perfectly interpolate the training data, then it would have plasticity equal to B. So it would be lower when it can't learn, higher when it can learn. It's focused on changes in the output of the network. So we're not measuring some internal quantity and hoping that it correlates with what we actually care about, which is the network's ability to learn. And it depends on the class of new tasks that we actually care about the network being plastic for. Yes. Yeah, so the question for people who are listening to this recording was, why don't we just look at the change in loss between the initial loss that we got from the parameters theta t and the final loss we get after running the optimization procedure to get theta star t. That is another thing that you could try to do. I guess the challenge there is, so like one sort of appeal, one way that we try to get around that is by sampling a lot of different tasks. So the idea is that like, even if you happen to get sort of a very low initial loss on one task, you're probably not going to get then a low initial loss on all of the tasks. So that's the strategy that we take, just because that way it's a little more robust to like statistical variance. Also, because you can imagine like if you start with a low loss, that kind of bounds how low you can, like what your delta can be. So then maybe a network that started off with a higher loss and then got to a lower loss, we would like say had more plasticity, even though maybe it's like they're both able to interpolate the data to the same extent. So we, for the most part, just try to sort of have this distribution of tasks be sort of uniform over the space that we care about. So in a lot of the examples I'm going to give later, the thing that we do is basically we sort of feed the outputs of a randomly initialized neural network into a sinusoid function, and we scale them by some very large scalar before we feed them into the random sinusoid. So the idea is that you're sort of sampling uniformly from the space of like all possible functions on some input set. And the idea is that like if you sample quite a few of these, then like there's no way that your neural network is going to get a low initial loss on all of them. Cool. I'm just going to make a quick note as well that one thing that I've been a little bit vague on is how we're sampling our inputs. So it might be that, I mean, in practice, what we really care about is, can our neural network minimize its test loss? This is like a great standard to use. For a variety of reasons, most of what I'm going to talk about in section at least 2 of this talk is going to focus on convergence just on the training data. Mostly because it's a lot easier to construct tasks that are very hard to minimize your training loss on, but maybe don't have enough structure to sort of give you a meaningful notion of generalization. Also, minimizing your loss on your training data is kind of a necessary condition to get a low test loss. And as we're going to see, there's a lot of examples where the neural network basically can't even minimize its training loss, let alone get a low test loss. So there's plenty of problems to solve in just the training loss regime. So just to give a few examples of how plasticity loss has sort of been noticed in the literature so far. One of the earlier examples that I'm aware of is this phenomenon called sort of warm starting, where basically the experimental setup here is you sort of train your neural network on half of CFAR10 for several epochs until you've basically got 0 training loss. Then you add in the rest of CFAR10, continue training for that number of epochs, and then contrast this with a neural network that just started from a random set of initial parameters in that second phase of training, and then was trained on all of CFAR10. And what they were finding was that there was actually a sort of non-trivial generalization gap that was coming up between the warm starting parameters and the random parameters. So this was mostly in terms of test accuracy that they were looking at. So what they were finding was both sets of parameters could minimize their training loss, but the randomly initialized network was much better able to generalize than the network that was trained on half of CFAR10 to start off. So this is sort of like one example of how the data you train your neural network on early on is very important. And it's particularly important to show your network a pretty large diversity of data when you've sort of randomly initialized it. It's worth noting, like, a lot of this is sort of, like, this effect is most prevalent in data sets where it's hard to generalize. So CFAR10 is like, if you don't use any regularization, your generalization performance is going to be terrible. There's like a lot of weird spurious correlations in the data set that you can latch onto. So this is mostly an effect that you're going to notice when there are a lot of spurious correlations that you have to worry about. And your network basically can't unlearn them. Another sort of known phenomenon that was first sort of identified by Agarwal et al. Is this sort of implicit under-parameterization effect, where basically The rank of your feature embeddings, if you look at the last layer of your network, will often decline over time. This is particularly prevalent in offline RL settings. And they notice that this decline in the rank of the features often corresponds to a decline in the performance of the network. I've also noticed a similar effect where when I was sort of playing around with these Montezuma's revenge agents that weren't learning anything, I sort of noticed a broader trend that if you sort of look at the ability of a neural network checkpoint that you've been training on RL to minimize the loss of some new regression task, it often gets worse at solving that new regression task over time. And I also found that this was the case even if you're just training on some sequence of random regression targets. So it gets harder and harder to learn sort of a new regression target if you have a sufficiently small network over time. There's also been a really interesting line of work sort of studying the primacy bias and critical periods. So the primacy bias is basically two observations. The first being that resetting parts of your neural network in RL can often help improve performance quite a bit. And this is sort of attributed to the sort of early training data that you're training your neural network on being kind of overfitted to in some sense and hurting your ability to improve your policy later on. I independently, in a totally unrelated project, had also noticed this effect where you can actually get quite striking visuals where if you pre-train a neural network on some weird pre-training data set, so here, for example, I was looking at high frequency versus low frequency sinusoids, and then you fine tune it on some other learning objective. So in this case, this was the value function you get from running a pretty good policy in Mountain Car. You can sort of see echoes of that initial pre-training objective, even once you've gotten quite low fine-tuning loss. And then the last example comes from some very unethical experiments in kittens, where they were basically showing that there's some very important sort of critical periods in the development of animals' visual systems, where they're sort of learning how to identify fine-grained details in images. And if you don't give them the right kind of image inputs during that critical period, they basically are never able to learn how to see properly. And then Achille et al. In 2017 were able to replicate similar effects in deep neural networks. It's worth noting that I've talked to some people who tried to replicate this and they had some difficulties. So I think it's a bit particular to their experimental setting, but it is definitely a phenomenon, at least in kittens. So now I'm going to talk a little bit about, given that we've seen plasticity loss happening in quite a few different instances, what are the mechanisms by which it occurs? So to study the mechanisms, I'm going to propose two model organisms of plasticity loss. So in regular science, people often use model organisms as sort of simpler settings where you can iterate a lot faster to sort of study a particular phenomenon. They're related enough to the subject you actually care about that you can reasonably, with reasonable probability, expect your findings to generalize, but you can experiment a lot faster. So the two sort of models that I'm going to be looking at are random label memorization with reshuffled random labels and sort of Q-learning on an image classification MDP. So this first model is not the most realistic, but it still captures sort of phenomena that could happen when there's some noise in your data distribution and that noise changes over time. And oftentimes your neural network will still try to interpolate that noise. So it's sort of identifying the pathologies that can come up from there being some very strong, very difficult to model correlations in your data set that sort of periodically change quite dramatically. So the idea here is we basically have some image classification data set. We uniformly at random assign some label to each image. Then after some period of time, we reshuffle these random labels. In the hardest example of this, we just don't pay any attention to what the classes of the original data set were. In sort of nicer versions of this, we might just shuffle the classes. So in MNIST, we might say all 2s are now 5s, all 5s are now 6s. Whereas in a really hard example, we might say each 5 is assigned a different label, which is very challenging for neural networks. The second setting we're looking at is sort of a very simple MDP where it captures the core of the RL problem, which has to do with the sort of distribution shifts you get from updating your target network and Q-learning. But avoids a lot of the confounding factors that you would get from exploration. So the idea here is we still want a rich observation setting where there's some meaningful thing that you need to learn. So we're going to use an image classification data set where we're going to turn it into an MDP by defining the state space to be all of the images in that data set, the action space to be all of the labels of that data set, and the reward function is an indicator of whether the action that the agent took when it saw this observation is equal to its true label. Then we uniformly at random sample a new state. So the idea here is that no matter what the agent does, it's basically seeing the same state visitation distribution. If we really want to sort of play around with the policy, we know what the optimal policy is, so we can sort of interpolate how often it explores versus how often it sort of takes the right action. And it's a sort of very natural form of non-stationarity because the only thing that's sort of causing the non-stationarity is the bootstrapping from the agent. So first, we're going to look at that random classification data set. Oh, yeah. Yes. Yeah. So the question was, isn't it just a contextual bandit? And the answer is it basically is. We're just adding bootstrapping. So yeah, the first problem that we're going to look at is sort of how neural networks can accumulate saturated units. So the figures I'm going to show right now are sketches. And then at the end, once I've explained what the experiment setup is, I'll show you what the real data was. So basically, one thing that you'll notice if you train a neural network to memorize random labels of a data set is that the accuracy will usually basically go to 100% eventually. But you often see this like initial spike in the number of dead units that it's then able to recover from and drop back down. But as we sort of iteratively shuffle the labels and ask it to train on new labels again, often these spikes get kind of bigger and bigger until eventually we hit some point where the network basically can't recover from these spikes anymore. The number of dead units stays fixed at some very high value, and the network accuracy basically drops to random guessing. So that's what the dark blue lines in this figure are showing. So here we see that like for the first couple of random shuffles, the network is able to get like basically perfect training accuracy by the end of training. But once we hit this point where we basically can't recover from these spikes in dead units anymore, we drop down to basically the accuracy of random guessing. Part of this is exacerbated by the fact that a lot of our optimization algorithms, especially adaptive optimization algorithms, assume some sort of like stationarity in the distribution of gradients, which we're violating here. So one in particular issue that comes up with Atom is if you look at the hypers for Atom, by default, your first moment estimator is updated very quickly, your second moment estimator is updated much more slowly, and your sort of correction terms to avoid dividing by 0 are very small. So this basically has the effect of saying, okay, well, when I change my task, my gradients are now really big because I'm very confidently predicting incorrect labels. So my gradients are really big. So my mean estimate goes up quite quickly. But it takes a much longer time for my variance estimate to go up quickly or go up at all. So what ends up happening is you have this very large number divided by a very small number. Your gradient steps are really big. And if there's already this sort of implicit preference of your network to sort of reduce the magnitude of the activations, then you're more likely to sort of take a giant step and kill off a unit in a way that's a lot harder to undo compared to if you took a very small step and it was sort of just barely dead. So the second class of problems that we were looking at, it's worth noting as well that if you sort of do a couple of fixes to Atom, so like you scale the updates on the M and V terms so that they're like more like updated at closer to the same time, you increase the value of epsilon. That removes this particular pathology that crops up after like 2 random shuffles. If we ran this for long enough, like way off the slide, like I don't know, somewhere over in the next room, the light blue line that corresponds to this tuned Atom would eventually start going down as well for like a more subtle reason. So part of this like more subtle reason is easiest to see in this sort of classification as an MDP model that we discussed previously. So in this particular case, one sort of cool experiment you can run is if you train a network with Q-learning, and then you want to test it on these sort of probe tasks that I mentioned earlier, where you're kind of memorizing random labels. You can look at the learning curve that you get from your optimization procedure on these new random labels. And basically, what you'll see is that when you take a randomly initialized neural network, it'll usually be able to fit the random labels pretty quickly, especially if you construct the random label memorization task such that it's feasible for a randomly initialized neural network to solve it. But as you look at sort of later and later checkpoints from your RL agent, you'll find that starting your optimization procedure from these checkpoints results in these sort of shallower and shallower learning curves, where it's a lot harder for the network to basically make consistent progress, reducing its new loss. So one thing that's sort of striking about this is that you might think, oh, well, maybe part of what's happening with plasticity loss is that networks are getting caught in bad local minima. This suggests that at least in the RL agents I've been looking at, this isn't the case. They're not getting caught in local minima because they're still able to reduce their loss. It's just that they're getting caught in some region of the loss landscape where it's a lot harder to consistently reduce your loss. So one thing that you might ask is, well, maybe this is just because we've devoted many, many decades to figuring out how to initialize a neural network. And our neural network initializations are like very special. So maybe this is just an effect of, oh, we moved away from our really nice neural network initialization. And the previous figure is just saying that as you move further and further away from a nice initialization, optimization just gets harder. So we tried to run an experiment that was trying to control for how far away you'd moved from your random initialization. So what we did is we sort of paired two update rules. So we followed gradient descent on the classification style MDP objective that we had before, where we're sort of fixing the target network for a while and then updating it. And then we compared that with this sort of paired trajectory where we basically did a random walk on parameter space, where the step size for each step of the random walk was matched to the size of the step that gradient descent took. So the idea is that at the end of this, both gradient descent and this random walk have sort of taken steps of the same magnitude, and they started from the same point. So in principle, they should be roughly a similar kind of distance away from a random initialization. And what we see is that for a lot of properties of the loss landscape, so here I'm plotting the distribution of eigenvalues of the Hessian on some new probe task. And here I'm looking at gradient covariance. What you can see is that the Brownian motion procedure looks very similar to the density. This is like an approximate. I'm using like a Lanczos method, so it's like not very good at catching like the middle of the distribution of the eigenvalues. But basically, like the overall shape of the eigenvalue distributions that we get from this approximation method are very similar. They're like a slightly scaled version, basically, of what you had at initialization for the Brownian motion. Whereas the gradient descent procedure, even though we're not looking at the Hessian on the task we were running gradient descent on, we're looking at the Hessian of a different task. It still has these like really big spikes and outliers that generally correspond to like an ill-conditioned loss landscape. Similarly, we see that like initially the gradients of a bunch of different inputs tend not to interfere with each other too much in either the neural network that we're going to train with gradient descent or with Brownian motion. But after we've trained for a while with gradient descent, we start seeing interference between gradients. So all the gradients are sort of becoming more collinear, whereas the Brownian motion is sort of maintaining a similar, effectively like sort of an empirical NTK compared to what we had at initialization. So we've seen that like the loss landscape changes. Both of the quantities that I was showing in the previous slide are very expensive to compute, and it's sort of annoying to try to come up with regularizers for them. So one thing that we wanted to look into is whether there's some sort of easier to measure properties of the network that are cheap to compute and that we can try to intervene on and expect to mitigate plasticity loss. So one thing that we tried to test for was basically, does it seem like there are any reasonable statistics of the network that are consistently correlated with plasticity loss under different types of experimental settings? So we looked at a few kind of plausible factors. So we looked at things like the norm of the weights, the rank of the weight matrices, the number of dead units in the network, and the numerical rank of the feature embeddings. We ran a bunch of different experimental settings where we varied things like the observation space, the architecture of the network, the reward function we were using in the MDP, and basically found that for any of these seemingly reasonable quantities that we might expect to correlate with plasticity loss, you could find one setting where they looked kind of positively correlated and another setting where they looked somewhat negatively correlated. So that's sort of suggesting that if we're trying to intervene on one of these to keep it either high or low, there's going to be some setting where it's not really doing the thing we want it to do with respect to plasticity. So we sort of end up with this slightly dissatisfying result, which is that it seems as though all trainable networks kind of have to be very alike because there's not very many ways that you can be trainable, but there's a lot of different ways that you can fail to be trainable. So somewhat dour conclusion, but I'm going to talk about a few examples of some really exciting works that are starting to address sort of maintaining plasticity in neural networks. I'm going to make a quick note, first of all, that in principle, none of these methods is going to be better than if you just reset your neural network every gradient update. So in principle, if you really want to maintain plasticity, just never train on anything, and you'll be fine. Obviously, this is not great because we want our neural networks to be able to learn things. So implicitly, we're sort of saying, we want to not slow down training too much, but we also want to maintain plasticity. So implicit in all the results I'm going to show are basically is this assumption that we want to maintain plasticity, but we're not going to do that in a way that makes training a lot more expensive or a lot slower. So right now, I would say gradient descent is sort of somewhere around here on this Pareto frontier. And the idea with coming up with methods that can sort of improve on this is that we want to push it closer towards this Pareto frontier. Once we're at this frontier, there's probably going to be trade-offs between sort of how much you want to sort of slow down training versus maintain your ability to adapt to new tasks. But we're so far from that frontier that at this point, I think we're still very much in a setting where we can kind of at least not hurt one while we improve the other. So I'm going to talk about a few sort of boring solutions that I found can really help maintain plasticity in neural networks. So there's sort of three very simple boring solutions that I found are quite effective. The first is to scale the width of the network. The second is to use sort of architectural tricks that are known to sort of make optimization easier. And the third is to use sort of nicer parameterizations of your learning objective that let you sort of learn things in a scale invariant way and give you smoother, better behaved gradients. So the first thing that you can do if you want to increase the plasticity of your network is just make it wider. There's maybe some interesting justifications for this in the context of sort of this line of work that's looking at sort of universal laws of robustness via isoperimetry, where the idea is that basically it's easier to interpolate your data with a smooth function if your network is wider. And in principle, if the function you've learned is smoother, it's probably going to have better behaved gradients and be easier to optimize in the future as well. So in general, widening your network makes it a lot easier to train it for a long time. The downside is that even if all we're doing is repeated random classification of MNIST, or we're doing even just learning image classification as an MDP, by the point where we're basically scaling to the width that will fit on a single GPU, we're still often seeing some non-zero plasticity loss. And I sort of am of the opinion that if you can't solve MNIST on a single GPU, then you're probably not going to be able to scale indefinitely for more complicated problems. So scale helps a lot, but probably won't be the single solution. Another thing you can try to do is to use a more stable architecture. So if plasticity loss is because the loss landscape gets harder to navigate, you can just use tricks that make the loss landscape easier to navigate, and you're probably going to see a lot of benefits. One thing that we tried that was particularly helpful was just using layer normalization. So using layer norm was super helpful in the two model organisms that we were playing around with before. We also tried just adding it to a DQN architecture and running it on Atari. And it was pretty much uniformly improving performance. When we looked at the sort of empirical NTK matrices that I was looking at before, where you sort of each point in this matrix is the dot product between a gradient of one state and another state, we see that the gradients are sort of more independent in the layer norm networks compared to in the networks that don't use layer normalization. And this is like, this distinction often corresponds to the difference between a network that can train and a network that can't train. And then finally, there's this really cool trick called the too-hot trick that you can also try to use, which basically turns a regression problem into a classification problem. This is particularly helpful for settings like deep-RL, where we don't know what the magnitude of the sort of final prediction we're going to want to output is. So we can often be in this position where like the norm of our outputs can get very, very large. The too-hot trick is basically a way of representing a scalar regression target as a distribution, where you basically define some support over all of the integers, and then you represent, or not all the integers, you sort of bound the maximum and minimum value that you expect the thing you're going to want to predict can take. And then you say, okay, I'm going to represent the number 7.2 as a probability distribution that assigns 80% of its weight to 7 and 20% of its weight to the number 8. And then I'm going to have my neural network also output a probability distribution, and I'm going to minimize the cross-entropy loss between the target and my outputs. So this has like inherits a lot of nice properties of classification losses. Softmax cross-entropy kind of gives you bounded gradients with respect to the logits, whereas L2 regularization does not give you bounded gradients with respect to your outputs. When we were sort of looking at this like MNIST and MDP style tasks, we were finding that the losses of the randomly initialized networks that were trained with this loss versus after, at the end of training, the gap in the sort of performance on these and the random label fitting tasks was a lot smaller than the networks that were trained with this categorical loss compared to ones that were trained with regression losses. So here, darker means lower, lighter means worse. So the darker figure here is basically saying that across a lot of different interventions and a lot of different architectures, you tend to see less plasticity loss if you use a categorical representation compared to doing regression. There's also a lot of fun solutions, which are actually trying to explicitly intervene on the network. So one thing you can do is try to reset the network and just like reset the whole network. So this is, again, like kind of it's a trivial solution in the sense that you're resetting the whole network. The thing that makes this technique non-trivial is how they're sort of able to get this reset network up to speed and actually able to generate useful data for their RL agent. So they have this particular teacher-student distillation procedure where they basically have a teacher that's acting in the world and a recently randomly initialized student that's trying to distill on the teacher's outputs. Once the student's good enough, they swap the roles to the teacher and student. The student's now acting, the teacher gets reset and is being distilled on the former student, now teacher's outputs. This they found was like fairly effective at improving generalization performance in sort of multitask RL. And it was often just sort of improving performance in general as well. If you want to be a little bit more targeted, you could try to reset a single layer. So this is work that Nikishin, Doro, and Schwarzer did, which they presented, sorry, this should be 2022, at ICML 2022, where they basically reset the last layer of the network periodically, and they found that this helped a lot in a variety of RL tasks. You can add another randomly initialized network to your parameterization. So the idea here is you basically take your original network, you freeze it, you add a new randomly initialized network, which you add a new randomly initialized network's outputs to the outputs of your original now frozen network. You train the parameters of this new network, and you also subtract whatever its initial output, the value under its initial parameters was. So the idea is basically after you add this network plus its like frozen initialization, you haven't changed the outputs of the original network, so your policy is still the same. But you now have this like extra new set of trainable parameters that have been randomly initialized, so hopefully still have a lot of plasticity. So in a lot of Atari environments, you can see that like when you sort of add this second network that's now trainable, you see these like sort of jumps in performance on top of networks that have like previously just plateaued. Another thing you can do is to reset units. So this was initially proposed by Dohar, Sutton, and Mahmoud, where they basically said sort of, if you reset units that aren't useful for some notion of utility, maybe we can sort of inject randomness into our neural network. And if these like new random features are useful, we'll keep them around. If they're not useful, we can reset them again. They tried this sort of continuous control task and found that adding in these unit resets helped a lot compared to just running standard PPO. If we want to, so like one of the challenges here is that they have this very complicated formula for computing utility. If you want to sort of make it even easier, you could just say, well, why don't we just reset units when they die? So this was presented at ICML this year by some folks at Brain Montreal. First author, Sokar, who I think joined recently. So what they found was basically, if you look at a sort of subset of Atari tasks, I think they were maybe looking at Minotaur. They found that basically resetting units that have died off can significantly improve performance over a sort of baseline DQN agent. Another thing you can do, and Marlos is here, so hopefully I'm not going to butcher this explanation, is you can try to, rather than resetting units that have died, you could just try to pick an activation function that isn't going to saturate in the first place. So there is some work by some folks at DeepMind and U of A, where they basically try to swap out a ReLU activation for a concatenated ReLU activation. So the idea here is rather than being 0 if the preactivation is negative and some linear function if it's positive, you sort of output a two-dimensional output of the activation where one dimension is going to be non-zero if the preactivation was negative, and the other one is going to be non-zero if the preactivation was positive. So you can basically never saturate. Always, at least one of them will be non-zero. This, at least in a lot of sort of, in this continual RL setting where they basically cycle through a bunch of different games and levels, was often like very effective at stopping networks from having their performance drop over time. Another thing you can try to do is regularize the features themselves. So rather than just doing like weight decay, which can sort of have some negative effects if you don't really get enough gradient signal from your loss, you could also just try regressing the sort of features towards their initial values. So if your features initially were sort of good enough to let you fit kind of anything you might be interested in, then if we sort of try to keep a random projection of these features to match what you were outputting at initialization, then maybe we're still going to sort of force our network to keep around enough of these like initial kind of good dimensions that it'll still be able to adapt to new tasks later on, while not interfering too much with its ability to learn on its current task. So we found that this was like quite effective, especially in settings like Montezuma's Revenge, at basically avoiding representation collapse. It seemed as though there's like a lot of sort of finicky things you have to worry about, like if I sort of have too many random projections that I'm trying to preserve, then like it slows down learning. If I don't have enough, then like it's not really going to have any effect. But at least in settings where you could get that balance right, it did seem to be quite helpful. So it's sort of inconclusive whether some combination of all of these methods will definitely solve plasticity. In part, this is because we often don't have a great counterfactual when we're evaluating them on what's the best performance we could expect to get if we completely eliminated plasticity. So like infer, so this is my method, so I'm free to sort of criticize it as much as I want. It definitely only mitigates plasticity loss. You can still come up with examples that are like, if you make your examples hard enough, then your network basically has no choice but to like totally erase all of its features and learn something that's like basically get into some region of parameter space that it can like not really get out of. A lot of the evaluations of other methods that I've discussed mostly look at performance. And then because we don't have a good baseline of like what it would look like to have completely eliminated plasticity loss, it's harder to tell whether or not they're like definitely eliminating all plasticity loss or whether they're just mitigating it partially. And in a lot of other examples, like you can still sort of come up with settings where, like, for example, if you reset units, that's great if your problem is that some units are dying off. But if your problem is some like higher level issue with the structure of the loss landscape, then resetting individual units might not be a strong enough intervention to help you like fully get over the issues that are coming up. So yeah, unfortunately, we probably haven't like totally solved plasticity loss, but we found a lot of really promising things that we can build on that all seem to be having beneficial effects. So I have like 5 minutes left, so I'm gonna go over the last bit really quickly. I think there are a lot of really interesting implications for larger models. So in general, sort of training a neural network on a harder task makes it easier to like really quickly induce plasticity loss. But I've not tried to run ChatGPT on my MNIST classification task, so I don't know. Maybe it would like never have an issue. Although my hunch is that like you can probably still come up with settings where if you're sort of training a large enough model, you would still run into some plasticity issues. There's also some implications of these findings sort of concerning pre-training and fine-tuning. So one thing in general is that training your neural network on like a bigger and more diverse task is usually better at sort of helping it sort of maintain plasticity than if you're training it on some very narrow task. So the sort of pre-training regimes that people have sort of settled on in the sense are probably very robust to plasticity loss because you're just training on a lot of different things at once. And you're mixing all these things together all throughout training. So your neural network sees everything from the start. It's possible, however, that like maybe if you get into the setting where you're like fine-tuning these networks not once or twice, but like 300 times, maybe the 300th time that you've fine-tuned a large language model, you're going to start to see issues with plasticity loss. That seems possible to me, but it's also not something I've really looked into yet. There's a huge gap here around the theoretical understanding of why neural networks lose plasticity. There's maybe some issues with signal propagation, but it's hard to say for sure whether the signal propagation issues are like the only thing that's at fault here. There's been a lot of like really exciting work on things like the edge of stability and neural collapse that might sort of have some interesting implications for plasticity as well. But again, it's sort of a very open field that I don't think many people have looked into yet. And finally, we don't have a great sense of like what the fundamental trade-offs are. So to some extent, there's probably going to be some tasks where no matter what you do, in order to minimize your loss on that task, you probably have to make your network slightly less trainable. But it would be really cool if we could say, here's exactly, like here's what these tasks are. So like there's maybe some settings where you just shouldn't bother trying to maintain plasticity because it's going to be impossible without interfering with your primary learning problem. But we don't really know what those are yet. So yeah, just to quickly conclude, plasticity loss is something that we've observed in a variety of contexts where non-stationary training dynamics occur. At least in some extreme cases, this can really have a big impact on the ability of agents to improve their performance on the tasks we're interested in. There's a lot of really promising approaches that exist to sort of mitigate or reduce the loss of plasticity. But short of completely resetting your network, we haven't found a single method that maintains plasticity indefinitely in any possible task you might care about. So yeah, that basically concludes my talk. Thanks everyone for your attention. I have 2 minutes for questions, I guess, if there are any. So I don't know of any non-gradient based optimization methods for, sorry? Oh, genetic algorithms. Yeah, I haven't really thought about genetic algorithms too much, mostly because like I don't really know of any that are practical to train neural networks with. If I had to guess, I would say that genetic algorithms still probably like they might run into issues of like sort of getting into a local minimum that's just like hard to get out of, sort of similarly to how neural networks can sometimes wander into regions of the loss landscape that are hard to navigate away from. But I don't want to, this is pure speculation on my part, so I won't waste people's time too much with my ill thought out ideas. Yeah, so maybe I'll just repeat the question for people who are watching the recording. The question is basically, why are most of the examples I listed in this talk in DeepRL and not supervised learning? And are there any sort of confounding issues that come up with DeepRL? So the answer to the second question is yes, there are a lot of confounding issues that come up in DeepRL that make it a very difficult setting to evaluate plasticity loss in isolation. The main reason why we mostly look at DeepRL is because the DeepRL setting is sort of the most natural form of non-stationary learning problem that we have available to us now. So it's possible to sort of construct continual learning benchmarks for supervised learning, but they all tend to be like a bit artificial. So in terms of like the types of settings where there's like a really large type of non-stationarity that's really fundamental to the learning problem, and is like really critical basically to being able to solve a like real task, that's mostly DeepRL. It runs into a lot of issues though, of course, because I mean, there's a lot of issues with like not instability, with exploration that are hard to isolate from plasticity, which is why I was also looking at like the sort of contextual bandit or sequential memorization of random label settings. But obviously, sequentially memorizing random labels is not the most compelling example. So it's nice to be able to ground it in something a bit more realistic. Yeah, that's an interesting question. So the question was basically how the sort of structure of the non-stationarity as it relates to sort of the complexity of the concept the network is learning relates to plasticity loss, and whether that might imply that certain layers are better to reset than others. I would say that there's some evidence. So the primacy bias paper does an ablation on this that's really nice. They look at the effect of sort of resetting individual layers. There was also a really cool paper I saw at ICML last month where they were looking at sort of where in a neural network does memorization happen, which sort of made me sort of rethink a few assumptions I'd previously had about how sort of there's this folk wisdom that like later layers memorize, earlier layers generalize, where it seemed to sort of throw a wrench a little bit in that assumption. So that paper is something about like localizing memorization, or can memorization in neural networks be localized? So that might be another thing to look at as well. So there are definitely prioritized sampling schemes that you can use. The most common ones we use in DeepRL tend to be ones that sort of prioritize samples where the network attained a sort of high TD error. I would say that you might be able to find ways of sampling that sort of give you more uniform distribution over everything that you could see. But I think there is this sort of fundamental issue that comes up in reinforcement learning in particular, where the agent only sees a limited subset of the world initially, and then it has to learn how to act in that limited subset before it can see more. So like if you're in Atari, you only see the first level initially, and then you see higher and higher levels later on. And there's not a great way of fixing that by a replay buffer unless you have access to a policy that can visit those higher levels from the start. So it's like possible that you could try to like improve the sort of uniformity of the state space that you're sampling from, but you probably won't be able to get around that second issue of just not having access to a policy that can reach those states in the first place. Yeah. So the question was sort of, when we're measuring plasticity, are we looking at sort of the current task or the current task and the previous task? And how does this relate to transfer? So most of the times when I'm measuring plasticity, I'm actually looking at plasticity with respect to kind of an arbitrary new task that we might want the network to solve. So in the case of the random label memorization supervised task, I can kind of get away with just looking at the current task because I'm implicitly defining the set of tasks I care about as a set of all possible random labels. So in that sense, each sequential task in that setting is kind of a new sample from that distribution. In the case of DRL agents, I'm mostly defining plasticity in terms of, can you minimize the loss on some new regression task? So in a lot of these cases, the measure of plasticity I'm using is completely independent of the network's ability to reduce its loss on its current task. And the idea is that because we don't really know what the next distribution of TD targets is going to look like, by having this like very sort of agnostic uniform distribution over targets that we're measuring, we're sort of saying like, well, if my neural network can minimize all of the loss on all of these, then it's probably going to be able to minimize the loss on the next set of TD targets as well. But if you could probably come up with smarter ways of measuring these things that are sort of more related to what the like there's a lot of structure in the distribution of next step TD targets that we're not taking advantage of in these evaluations that you probably could. In terms of transfer learning, I think so that's definitely related. I think because in a sense, we are looking at like how quickly can you transfer to a new task. Mostly with transfer learning, you're looking at tasks that are related in some way. Whereas here we're a little bit more agnostic. And the phenomenon that we're interested in studying is basically just, are there ever instances where if you train on one task and then you want to fine tune on another task, are there structures of that initial training task that basically prevent you from ever being able to minimize the loss on another task?